let's go ahead and get started. Any questions about anything before we finish up our chapter 7 here? All right, and I'm feeling it, almost the end. So 2 more weeks of lecture. Just make sure you get all those assignments in. That's the big thing I have to say. So I'm accepting late work from everybody. So just get those in. You don't have a bunch of zeros to hurt your grade.
Is it just me, or are we missing a few people?
Every day we're always missing more and more, it seems. I think the gas prices aren't helping anyone either.
Okay, so which of you 3 are going to show up in the next lecture then?
All right, so let's look at phase changes while we take bets on who's going to drop out. So phase changes, so we can do phase changes can be induced by heating, cooling, or changing pressures. And you're probably, at least generally, aware of this. Again, you're probably familiar with ice. So you can take ice out of the freezer, and then it sits out on the counter, which means that it's getting, of course, heat from the surrounding atmosphere. So then heats up that solid ice, gives it energy, brings it to liquid on your bench top. And then, of course, you could take that water and add some more heat to it. Let's say you put it on the stove. And then, of course, you'd get your boiling water like for pasta or whatever. And you get that gas in the form of steam. And so now let's dive in. And so what actually dictates the boiling point? What holds molecules together? And so what holds molecules together are these intermolecular forces. And so notice inter, kind of like the interstate highway where it's between states. Inter means between molecules. So that's kind of the key thing. And so when we're doing these state changes, I want to really emphasize, right, we're not breaking bonds or anything. This is a common mistake that students do in like the language. But we're just kind of separating these intermolecular forces, these molecules, when we add energy. And so all attractive forces between particles are electrostatic in nature, and we'll kind of look more at what that means, but we know electrostatic means that we kind of have to have opposite charges or some sort of dipole moment, something to bring things together. And then so the strength of these attractions, though, between the particles, that's what determines its state. So again, at ambient temperature, the fact that nitrogen is a gas depends on those intermolecular forces, just like water is a liquid at ambient temperature. And so at room temperature, moderate to strong attractive forces result in materials being solids or liquids. And so the stronger the attractive forces are, the higher the boiling point of the liquid and the melting point of the solid will be. And that makes sense, right? So stronger intermolecular forces, then it's going to take more energy to kind of break them apart and get them into their next phase. And so attractive forces vary in strength. So we'll look at kind of the 3 main categories and how to rank them. And of course, the stronger the attractive forces between the particles, the more the particles resist moving. And like we've already mentioned before, so no material completely lacks particle motion unless, of course, we're at absolute 0. And so the stronger the attractions between the atoms or molecules, the more energy it will take to separate them. And so when we boil a liquid, we have to add enough energy then to overcome those attractions then between the particles. And again, it emphasizes here that we're not breaking any bonds, we're just disrupting those intermolecular forces. And so it would take more energy then to break like a covalent bond. And so again, the higher the boiling point, of a liquid, the stronger the intermolecular attractive forces. And so now, why are molecules attracted to one another? So we mentioned they have to have those electrostatic interactions, and so this means that intermolecular attractions are due to attractive forces between opposite charges. And so we've seen this before with an ion, like a cation and an anion in an ionic compound. Or we could see it in, for example, a polar molecule. And so this is where determining dipole moment will kind of come back. And then even nonpolar molecules will have temporary charges, and we'll look at what it means by this instantaneous dipole. And so a larger charge means a stronger attraction, and a longer distance means a weaker attraction. So let's start with dispersion forces. So these are the weakest, and so you may also see them referred to as, so they could just be plain dispersion forces. Sometimes you see their full name, London dispersion forces, or another name for them is van der Waals. And so the most important thing about dispersion forces is not only are they the weakest, but all molecules and atoms will have dispersion forces. And so all the dispersion forces is it results from the temporary charge based upon the electron density. And let's look at the diagram, because the picture is a better representation. So here we have little helium atoms depicted here. And so helium, right, has 2 valence electrons. And so just imagine, this is a snapshot here. And so our electrons are floating around, floating around. Well, let's say we just pause it. And so if we take this snapshot here, we see we have our 2 electrons just happen to be on the left side here. And so that means just temporarily we have a partial negative charge here. And there's no electrons on the right side, so that means it gets a partial positive charge. And then notice how if the neighbor is experiencing that same sort of thing, where it just so happens now the electrons are over on this left side close to this region of positive electron density, or a lack of electron density. So now there's going to be a charge here, so we have opposites attract, and so now we have our van der Waals forces here. And so, right, obviously this is fleeting, temporary, and those electrons are going to keep moving, but then you'll keep getting that small dipole moment, again, as these electrons float around. So now, right, maybe they can move to this side, they'll move to this side, and then you'll kind of have the same thing again, where you get a temporary charge, but maybe the partial positive is on the opposite side, you know, your partial negative will move, etc. So these will, again, kind of move around. And so that is why they are the weakest, because again, they're just from those fluctuations in electron distribution, which gives you a temporary or instantaneous dipole. And so like we noted in the graph, the region with excess electron density has a partial negative charge, and so that's indicated with that symbol. And the region with depleted electron density has a partial positive charge. And so let's look at how size affects the dispersion forces. And so as our molar mass increases, the number of electrons increases, and that means that you have a larger electron cloud, and so therefore you have kind of more electrons that can be polarized, and so the strength of the dispersion forces increases. And so, again, the stronger the attractive forces, the higher the boiling point. And so now we can look at this trend with the noble gases. So looking at helium, so of course it's the smallest with a mass of 4 grams per mole. And then notice its boiling point is like 4 Kelvin, so extremely, extremely low. And then so neon, a little bit larger, right? More surface area, more larger electron cloud. And so it has a slightly higher boiling point. And then you can see this trend kind of continue all the way up to xenon. It's now a larger mass of 131, but then still a relatively low boiling point of 165 Kelvin. So the other thing that will affect the strength of our dispersion forces is the shape. So again, how much surface area they have to interact. So if we're comparing, so this is N-pentane. We can also kind of abbreviate N-pentane like this in its little skeletal structure. So each little point is a carbon. And so notice with the pentanes, so it's kind of drawn here. We can see in this little depiction as well. So they can stack up really nicely. So you've got a lot of surface area for those intermolecular forces. Versus neopentane. So neopentane still has 5 carbons, but now you have a carbon in the center with attached to a bunch of other carbons like this. Trying to draw it in 3D for you. And so if we think about how those are going to interact, you of course notice right away that there's a lot less surface area. So now you're trying to like interact these two compact structures. And so again, as shown here, you have a small area for interaction. And so we would expect then pentane to have the higher boiling point. And yes, indeed, that is true. And so notice the only factor that we're comparing is their difference in geometry, since they have the same molecular formula, so they're all C5H12. And you can see that in the molar mass. So exact same molar mass, so that's not influencing the difference, but instead just that shape. And again, that's 36 degrees Celsius for the boiling point of pentane versus 9.5 for neopentane. And so as you might imagine, if we were to look at a graph then of the boiling point of our N-alkanes, so these are all just straight chain alkanes, notice their boiling point increases as you continue adding carbons, so the chain gets longer, higher molar mass, they also have more surface area, and so that boiling point just keeps increasing. And so again, branch chains will have lower boiling points than straight chains. So now the next intermolecular force are going to be dipole-dipole interactions. So now these are stronger than our van der Waals. So now they're, we'll say, what should we say, second strongest. Or I'll just add stronger than our van der Waals. So this is the next one. And so with these dipole-dipole interactions, what they depend upon is our polar molecules. So previously, we had kind of seen how to identify polar versus nonpolar. And so if you have a polar molecule, that means that it has a permanent dipole, and you also have some sort of unevenness where you have, greater electron density on one side versus another. And we saw again how that was related to the individual bond polarity. So first we have to determine, is our bond polar? And then is our shape asymmetric such that the polarities do not cancel out? And so that gave us a polar molecule. And so let's look at an example here. So we have, I believe this is acetone. And so this would have a permanent dipole here, so we have oxygen on one side. I think it's best depicted by this electrostatic potential map. And so notice the red region is our region of high electron density. So surrounding our oxygen, we could also draw in our two lone pairs on oxygen, just to emphasize that, yes, this is where our electron density is. And so what we can also do, I don't know if some of y'all are going into OChem later, but we can also draw a resonance structure that emphasizes kind of the partial charges. So if I just kick these electrons up, I could write this resonance structure. And so that leaves oxygen with a negative charge, and then this carbon has a positive charge here, so obviously it's missing bonds, so that's not great. But what we're going for is that this carbon then has a partial positive charge, since it has less electron density, and that oxygen again can take that electron density. And so now if we put two of these molecules together, we see that our negative end is going to be attracted to this partial positive here. And so you can see this, I think, best represented by this picture here. And so they would be oriented, right? Again, you have your partial negative charge on your oxygen, and then that's going to be attracted to this partial positive of our carbon here. And again, since it's a permanent dipole, then that interaction is going to be stronger than our van der Waal. And so this permanent dipole adds to the attractive forces, and we still have van der Waals, so those are still in this molecule, right? So we still have our temporary charges that are going to hold it together and that are dependent upon its molecular weight and its geometry. But now we're just adding the influencing factor of our permanent dipole, and we see how it raises the boiling and melting points of polar molecules relative to nonpolar molecules of the same size and shape. And so what they mean by that is if we just compare formaldehyde and ethane, so different formulas, but their molar masses are about the same. So we might expect them to have similar boiling points, except that the boiling point for formaldehyde is negative 19.5, versus ethane, that's negative 88 degrees Celsius. And so you can see the formaldehyde has a relatively much higher boiling point than our ethane, simply because of that dipole moment. And of course, ethane, right, this would be nonpolar, so it only has the van der Waal forces. And so now we kind of look at this dipole moment versus boiling points. This is a good comparison. And so if you ever wanted to look at the dipole moment of something, you can always look on like Wikipedia. And so this will give you like the experimental number of how polar a molecule is. And then what's also relevant in this graph is that we're comparing molecules of very similar molecular weights. Since we don't want to look at the factor of the van der Waal forces, we just want to see how the boiling points increase as we increase the dipole moment. And so you can see that if we start off with propane, so propane, nonpolar, you can see that in its dipole moment, 0.08, and so it has a boiling point around 220 degrees Kelvin. Now ether, so ether, dimethyl ether, has an oxygen in the center, so now it's like a little bit polar. You can see that in our dipole moment. So slight increase in boiling point. And then ethylene oxide, so let's zoom in so you can see these a bit better. So now this ethylene oxide, again, now it's a little bit more polar than dimethyl ether, since you have this little epoxide ring with our oxygen there. Again, you can see our electron density is located there. So again, increasing boiling point. And then our acetaldehyde, now we have our oxygen kind of on the end of our molecule, so greater dipole moment. And then now we can compare that to acetonitrile. And so now our electron density is over here on the right, partial positive on the left, and this has an even higher boiling point, of now 350 Kelvin. And of course, acetonitrile has the highest dipole moment of about 3.92. So now we can look at hydrogen bonding. So hydrogen bonding is now a special type of dipole-dipole interaction. So hydrogen bonding, this is also the strongest intermolecular force. Unless you're considering like ions in solution, but for the most part, it's usually referred to as the strongest intermolecular force. And so this is a special situation where you have hydrogen bonded to either oxygen, nitrogen, or fluorine. So it's only in these specific cases. And the reason why it happens is because we have a very electronegative element bonded to hydrogen. And so that means it's essentially stripping hydrogen of all its electrons. And then of course, if you recall, right, hydrogen just had one little electron to begin with. It gets pulled over. And so now we can say that the nucleus is de-shielded, aka that H proton is exposed. And so that means that then it can act as a strong center of a positive charge. So you would put your partial positive charge around that hydrogen. And of course, that would attract the partial negative charge of your electron clouds from your neighboring molecules, such as your neighboring water molecules. So here's kind of our electrostatic potential map. Again, just looking at this hydrogen bonding, it's like HF, so very strong intermolecular forces. And so if we look, let's look at ethanol first. We can see here we have our two molecules of ethanol kind of oriented how they would go. So here's carbon 1, carbon 2, and then our OH of ethanol. And so notice this hydrogen, so you can draw in your electrons again. So we have our partial negative charge here. This leaves our hydrogen partial positive. And then it's going to kind of line up with the other oxygen of ethanol. So it's attracted again to that partial negative charge. And then this other hydrogen, of course, has a partial positive. And so we could go kind of on and on and on where they're all attracted to each other. And so let's draw it out for water. So water, again, we would have similar effects, except now we have two hydrogen bonding scenarios, right? So both of these hydrogens have a partial positive, so both of them are being stripped. Of course, this oxygen, partial negative, and then of course another molecule of water can come along, that negative, the negative electron density would of course be attracted to our hydrogen here, and then we could continue on here. And so again, hydrogens are a very strong intermolecular attractive force, stronger than both dipole-dipole or dispersion. And so substances that can form hydrogen bonds will have higher boiling points and melting points than, again, some substances that cannot. And this is just emphasizing that, again, we're coming nowhere near the strength of chemical bonds. So even though we're emphasizing how strong this hydrogen bonding is, it is still only 2 to 5% the strength of a covalent bond. And so if we want to compare our boiling points again, so now we're looking at ethanol versus dimethyl ether. So dimethyl ether was in our previous example of having a dipole-dipole moment. And so, right, this was polar. We had our oxygen here providing our negative electron density and making this side of the molecule, again, have a negative charge. But even if we compare it to ethanol, so again, similar molar mass, so that's not a factor. But then you can see this huge difference in boiling point. So dimethyl ether has a boiling point of 22 versus ethanol of 78. And so let's look at this graph here, because this is also pretty interesting. So we're looking at the boiling points of group 4 and group 6, kind of comparing. And so what do you notice? What's our anomaly here? So which one sticks out on the graph?
Water.
So water. So why does water stick out? What makes it special?
Highest boiling point?
So it has the highest boiling point, but why is that?
Because it only has 2 hydrogens and 1 oxygen.
And then, so what kind of bonding does it have?
Hydrogen.
Yes. So it's the only one with hydrogen bonding. So it's the only one. So again, it's that special scenario. And so all these other ones, right, they just follow kind of the general trend. Methane, if you recall, right, this is nonpolar. All these are nonpolar. Oh, I see it in the chat too. So hydrogen bonding and polarity. Exactly. So all these group 4 are nonpolar. So they're down here. And then, so group 6, so these ones would be polar. Right, so hydrogen sulfide, so that's polar, but it does not compare to the strength of that hydrogen bonding. And so water, again, has a much higher boiling point than we might expect if it was just based off of molar mass alone. And so a similarly related property is surface tension. And so surface tension is just a property of liquids that results from the tendency of liquids to minimize their surface area. And so you see kind of droplets maybe form a little spear. And so the surface tension of a liquid is the energy required to increase the surface area a given amount. And so if you kind of compare these two, so comparing water to C6H6, which I'll tell you what that is. So that's just benzene, which is this aromatic compound here. So it's organic. And so we see, again, water has a higher surface tension, all related to its stronger intermolecular forces. And so now we know, so the stronger the intermolecular attractive forces, then the higher the surface tension. And so have you ever done like those penny experiments where you try to see like how many, drops of liquid. I don't know if have you just done it with water? I don't know if you've ever tried it like isopropanol too.
Yeah,
Or
we tried it with water, and then I think what we did was we added like, what's something that like destabilizes the bond between them? Like add a drop of oil or something, was it?
I don't know what you did. It could be like soap or something.
Oh yes, soap, duh. We just like added a tiny drop of soap or something, and then it just fell.
That's funny. Yeah, so it's the same sort of concept. And so, right, you can see that with the penny. So there's my penny. And you can get a nice bubble for water, especially if you go nice and slow, since it has really strong intermolecular forces. But then if you try to do the same with just any like organic solvent, isopropanol, ethanol, then you'll find that that has a much less tendency to kind of bubble up. So you can probably get less drops on there. And then, so another thing that will affect the surface tension is the temperature. And this makes sense, right? So you have your intermolecular forces kind of holding everything together. But then if we raise the temperature, now we're starting to introduce kind of molecular motion, increase that kinetic energy, and so then that's going to start to disrupt that surface tension.
I mean, to be fair, ice has really high surface tension. Like, it just doesn't want to fall apart.
Well, then that wouldn't be surface tension, though, because it's not a liquid.
What isn't it?
Not until it does a phase change.
No, I'm talking about liquid ice.
There's no such thing. All right, so then we have our surface tension. So this is, of course, what allows you to float different objects on, or that little bug that can kind of spread out and stand on the water. And so again, all that is because of those cohesive forces that keep everything held together, even though there's something else kind of pressing down on it. And so you can float a paper clip, even though steel is denser than water, the surface tension will keep that little paper clip afloat. And so another related factor is going to be vapor pressure, which makes sense since that's related to boiling. And so the pressure exerted by vapor when it's in dynamic equilibrium with its liquid is called vapor pressure. And so all that means is you have your liquid and there's some sort of equilibrium of molecules being deposited and molecules evaporating. And you probably know this, right? Like if you have an open system of water, for example, eventually it's going to evaporate, even though the room is not at its boiling point of 100 degrees Celsius. You're just losing some if you have an open system. Or you may also notice this, I know a lot of you are probably too young to drink, but if you like open up the alcohol and you get hit in the face with those vapors, right? It's just because ethanol has a lower boiling point, so they really hit you in the face.
Or really not wanting to leave high concentrations of ethanol just sitting out without being covered because the gases can fill the room and then a single spark can kind of cause an ignition, which is usually pretty bad.
Yeah, I don't think ethanol will get that bad, but it is a big flammable hazard, and you could have like a little bit of vapor of ethanol like start a fire.
I mean, isn't its flash point fairly low at only like 55 degrees Fahrenheit?
Probably, but yeah. I was saying you probably wouldn't fill like a room with it.
Well, you wouldn't fill a room, but it could definitely be not so good. You definitely don't want to work in an open and closed space.
Yeah, and I mean, it is obviously pretty flammable too. But something else that'll like hit you in the face are like diethyl ether or just ether. Like if you ever open one of those ether drums on a hot day, it will definitely hit you in the face with that vapor pressure. And although you do bring up good safety points about ethanol, because I think that's one of the bigger hazards that biologists face is they're like cleaning and sterilizing things with ethanol in an open flame. And so, of course, that's a good formula to light your whole ethanol bottle on fire, if you're not careful.
You know, for scientists, that really isn't very smart of them.
I've heard of it happening. And so going back to vapor pressure then, as we're kind of alluding to, so the weaker the attractive force is then between the molecules, the more molecules will be in vapor. So that's why I was bringing up that ether is going to hit you in the face kind of more. And then even ethanol will hit you in the face, you know, kind of versus water. And so again, the weaker the attractive force is, then the higher the vapor pressure. And the higher the vapor pressure, the more volatile the liquid, so the more that it's going to evaporate, and of course, maybe present a flammability hazard if we're not too careful. All right, so now let's get into the math of it. And so this is the energetics of melting. So when the high energy molecules are lost from the solid, the average kinetic energy of lower. And so if energy is not drawn back into the solid, the temperature of the solid will decrease. And so melting is an endothermic process where you have to put energy into the system. And then freezing is an exothermic process, so heat has to be lost and go to the system away from, to the surroundings away from the system to freeze our system. And so melting, again, requires input of energy to overcome those attractions then between the molecules and break those intermolecular forces. And then, so when we heat a solid, its temperature will increase until we get to the melting point. And so this is how much heat can be added. So this is our heat capacity is equal to mass times the specific heat times our change in temperature. So this would be for our heating. Heating, and by this I mean changing temp. And so you'd have to look up your specific heat for each substance. And so this would be on this curve. And then once the temperature reaches the melting point, then all the added heat goes into melting the solid. So notice from here to here, we have a plateau, right, of our temperature. So there's no temperature change, and instead this is telling you that a state change is occurring. And so, of course, this would be our state change since we're looking at water. So this would be, of course, going from solid to liquid here.
Is it a peaceful transfer of power, or is it a coup?
It's always peaceful.
Got it. So for molecules, changing of the state is peaceful. Humans could learn a thing or two.
And then, so once, right, it's all converted, then you would have to find your new specific heat for now liquid. So this would be example specific heat for solid, ice. And then for this part, we could once again figure out how much heat based off, again, the specific heat capacity for now liquid water. And so we all know that ice water will always have a temperature of 1 degree Celsius. And so heat of fusion then is defined as the amount of energy required to melt 1 mole of a solid. And so again, every substance, you would have to look up the heat of fusion. And so looking at water here, so we can look at our heat of fusion, so it's roughly 5 point something. I'd have to look at the exact value, or 6. So roughly about 6 kilojoules per mole. And so again, melting is always endothermic, so if you're going in the forward direction of converting ice to liquid, then you know you're adding heat. If you're going the reverse, liquid to solid, then the delta H would be the same, it would just be negative. And so that's emphasized here. So your heat of crystallization is just then the opposite of the heat of fusion. So you would have to lose that same amount of energy. No, we didn't. And so let's add under here. So we also have on this chart our delta H vaporization. And so that's just defined as the energy needed to go from the liquid to gas state. And so you can see how much larger your delta heat of vaporization values are. So water's, somewhere around 40 kilojoules per mole. And then, so do you all know what sublimation is?
Sublimation, is that where it goes directly from a solid to a gas?
Exactly. So sublimation, solid to gas. So if you wanted to find out how much energy it took to do that transformation, if you're not given a delta H sublimation value, then it's just the same as adding the heat of fusion value plus the heat of vaporization. So for water, it'd be at like 46 kilojoules per mole or something for sublimation. All right, so now we'll go through this whole heating curve of water kind of step by step so you know how to do it. And so our overall goal of this transformation here is we're going to start at negative 25 degrees Celsius of solid ice, and then we eventually want to go all the way to 125 degrees Celsius for our steam here. And so let's start that. So again, first step is just to heat our 1 mole of ice at negative 25 degrees Celsius to our melting point. And so again, that's just given by this. So our heat needed is equal to mass times our specific heat of ice times our change in temperature. And so they have all the numbers here, but let's just kind of go through them. And so the other tricky thing is looking up the specific heat and making sure that it matches with whatever units we're in. So in this case, we're given a mole, but our specific heat of ice is given in joules per gram degrees Celsius. So we would have to convert this moles to grams. So of course now that's 18 grams. But then now we can plug it into our formula. So we have 18 grams times, again, our specific heat, which is just a standard you would look up. So times 2.09. And notice this is joules, because if you recall, our heat of fusion and vaporization were given in kilojoules, so much larger. So just keep an eye out for that. And then times our change in temperature, so we know we have to bring it to the melting point, because at that melting point we have to stop and figure out the energetics of that leg. And so as we go from negative 25 to 0, that's a change in temperature of 25. And of course you can plug it in. I'll just plug it in so we're all on the same page. So 18 times 2.09 times 25. And so that's how they got this 941 joules. Or they went ahead and converted it to kilojoules, so 0.941 kilojoules. All right, so that's leg number 1. So right now we're here. And so now we have to do the energetics of melting. And so you would look up your heat of fusion for your substance. And so again, we're at our melting point for water. Look up your fusion for water, so it'd be 6.02 kilojoules per mole. So now we're in units of mole. It's fine to leave this as mole. And so now this is just equal to N times our delta H of fusion. So that just gives us 1 mole times 6.02 kilojoules per mole. So we just needed 6.02 kilojoules for that transformation. All right, any questions on that leg? So we did 2, so that was our 6.02 kilojoules. So now we're at leg 3. So now we have 0 degrees Celsius water, and we need to take it to the boiling point. So we need to take it to 100. So we have to use that heat capacity formula again. So same formula, Q equals our mass times our specific heat times our change in temperature. Except this time, so now our specific heat of water when it's a liquid, slightly higher, so 4.18 joules per gram degrees Celsius. So once again, we take this 1 mole, bring it to 18 grams. So we're in the right units. Then we know we have a delta T of 100. And so that's what they did here. So let's just plug this in. So 18 times 4.18 times 100. And again, this is in joules. And so that we can convert it to kilojoules. So that gives us 7.52 kilojoules. So now we've brought it to the boiling point. So now it's time for this segment 4 here. So now we need to take our liquid water and vaporize it all. And so since we're vaporizing, going from liquid to steam or liquid to gas here, you find your delta H of vaporization. So your delta H of vaporization for water, we said that was 40.7 kilojoules per mole. So now mole, we can just multiply those two numbers. So 1 mole times 40.7 kilojoules per mole just gives us 40.7 kilojoules. So that's how much energy was added there. So you can see how much more that energy was in comparison. And now, so at our last leg, right, so we've heated up our water, we vaporized it, so now we have a bunch of water vapor at 100 degrees Celsius. But we want to bring it to 125. So once again, same formula, all right, Q equals mass times our specific heat, so now we have to find it for steam, times our change in temperature. So our specific heat for steam is 2.01 joules per gram degrees Celsius. Moles, we need in grams again, so 18. Our delta T is just 25 as we bring it to our final 125. And so we can see how they got their final value here. Oops. I'll just plug it in so we're on the same page. So 18 times 2.01 times 25. And so that gives us 905 joules, or converted it to 0.904 kilojoules. And now kind of the final question would be, so what was the total energy required to go from negative 25 degrees Celsius ice to 125 degrees Celsius steam? And of course, to answer this, now we just have to go back and add all the little components up of each leg. So let's start back at segment 1 here. And so we have, and just make sure you're in the same unit. So I'm going to go with our kilojoule number here. So 0.941 kilojoules for our first leg, plus 0.02 kilojoules for a second leg plus 7.52 kilojoules for segment 3 plus 40.7 kilojoules for heating up that liquid to steam, and then the last segment plus 0.904. And so that would give us a total energy of 56, and let's see, we'll round it to 3 sig figs, so 56.1 kilojoules. So any questions about that? I know it's a little fast. But it's all just kind of repeated of the same formula. So just kind of a recap, right? This is always a formula that you're going to use to figure out kind of how much energy it takes to do the temperature change of mass times whatever specific heat of your substance times your change in temperature. And then anything else when you're doing the state changes, that's where you want to go back and reference either your fusion from solid to liquid or liquid to solid, and then vaporization for liquid to gas or gas to liquid. So I think that actually finishes up the chapter. Let me pull up, grab your homework. So any questions so far of anything?
Do a couple examples.
Of and what? Sorry.
Well, we just did in section 9, but
Oh, so just the state change stuff? So you want to do more?
1 or 2.
So I was looking at your homework. So there shouldn't be anything too difficult there, as long as we're feeling good about the whole kind of PV equals nRT stuff. Sorry, I'm trying to find an example. Trying to do one that's not water, but trying to find all the, there we go. So let's see, so acetone has a delta H of fusion of 5.7 kilojoules per mole. hoping for heat of vaporization, but that's okay.
Questions this?
I'm just making up a question.
Oh,
Oh, there's the delta H of vaporization. And the delta H of vaporization is about 30 kilojoules per mole. And we need specific heat of acetone. And so the heat capacity for acetone, so our heat capacity for a liquid of acetone is 124.5 joules per mole Kelvin. And you have to watch the units on these because, again, you could look it up and be given them in different units. I was hoping for solid heat capacity, but I guess not. And so we'll do gas heat capacity is apparently 75 joules per mole Kelvin. And sorry, you need a lot of information to do these problems. And the boiling point, if I can find my mouse. And the boiling point is 329.2 Kelvin. I'll add in melting point. So melting point, 178.25 Kelvin. So let's see. So let's just say, what's 178 Kelvin? That's pretty low. So we'll probably just look at liquid acetone. But let's just say we want to take acetone from 0 degrees Celsius. So we have to do some temperature conversions. To 100 degrees Celsius. And so what heat would be required? So I'll give everyone at least a couple of minutes to get started on that. And then we'll start kind of going over it, kind of laying out like how you should structure it, how you should think about it, and how to kind of approach these problems. Oh, and you probably need an amount. So let's just do 1 mole of acetone to make it easy. right, so let's at least start kind of working through this, and you can let me know what you've done. But what I would kind of do is at least set up like this little diagram, because I think this is super useful. But what you want to do is just kind of change the parameters so that it's for acetone, because you can obviously see, right, our melting point for water is here, boiling point for water is at 100. So let's just kind of redraw this, but then set all our parameters for acetone, and then of course do our temperature conversions and all that. And let's see, so I don't want to be in Kelvin. So I want to convert my melting point. So 178 Kelvin. So our melting point is negative 95 degrees Celsius. And it's kind of irrelevant for this problem, but it's at least good to note. So we're starting kind of way above the melting point, so we don't really care about the heat of fusion. It's already a liquid. And the boiling point, so we can just subtract minus 273. So we're at 56.2 degrees Celsius for our boiling point. Okay, so now I'm kind of looking at the problem. So we're going to start off at 0 degrees Celsius, and so it's going to be a liquid. And then we're going to go from 0 to 56 to our boiling point, and then do the state change, and I'll have to take that liquid or gas acetone and raise it to 100. And so I'd probably again sketch out our little graph. And this is more just for me, so I know, okay, it's going to melt negative 95 degrees Celsius. There's our melting. So melt. Then it has our liquid phase. So all the way to 56. I didn't really give myself enough space. Then we'll do our transformation. So this would be our heat of fusion, heat of vaporization, and then we'll take 56.2 all the way to 100. And so let's look at this. So we're starting kind of at 0 over here, somewhere in the liquid phase. So what do I need to do first then? I got all these heat capacities. So what do I need to calculate? So what should be the first thing that I'm calculating then?
The amount of energy you need to go from liquid to the boiling point.
Exactly. So we're at 0. So we want to go from 0 then to the boiling point. So that's 56.2 degrees Celsius. And so that means I need my heat capacity formula. So Q is equal to MC delta T. At least that's our standard. But in this case, I didn't mean to trick y'all. It was just more, this is what the internet gave me. And so instead of mass, we can just use moles, because again, use your dimensional analysis to kind of figure out. And then still moles per Kelvin. Remember, Kelvin and Celsius go up at the same rate, so that's fine. And so let's use then our heat capacity for liquid, and so that's 125 or 124.5 joules per mole Kelvin. And so in this case, even though, again, we'd seen mass before, that's just what water tends to be given in. So in this case, we'll keep it in moles. So times 1 mole, since that's the amount we were given. And then our delta T then is just 56.2. And so let's plug that in to our calculator for our first part. So 124.5 times 1 times 56.2. So then we get, and this is in joules, I'm going to convert it to kilojoules. So this gives me 6.99 kilojoules then. So now we've heated our acetone from 0 to 56. So now we're here. And so now we need to figure out how much energy it takes just to do that state change. So let's do that. So now it's state change time. And so we're just looking at liquid to gas now on this leg. And so for that, we need our delta H of vaporization, so 30 kilojoules per mole. We kept the math easy, so 1 mole, so that's just 30 kilojoules per mole times 1 mole. So this gives us 30 kilojoules in energy we needed. So now we've just done the transformation. So now we have a bunch of gaseous acetone sitting at 56.2 degrees Celsius. And then the last part asks, well, let's take it to 100. So now let's go through that last bit of transformation. So now we need to take our gaseous acetone from 56.2 degrees Celsius all the way to 100 degrees Celsius. So we need that formula again of our heat capacity. Q equals our MC delta T. And so we look up our heat capacity for gas, the gas phase of acetone. So this is 75 joules per mole Kelvin. Again, a little bit different from our formula, but that's why you just have to watch your units. I already forgot the number by the time I scroll down. 75. So 75 joules per mole Kelvin. Now instead of plugging in mass, we'll just plug in moles. So 1 mole times, so our delta T, which I want an actual number, so that's 100 minus 56.2. So that gives me my delta T of 43.8. So now just plug that in. So 43.8 times 75 then times 1 mole. So that gives us, and let's put that in kilojoules. So that'd be 3.29 kilojoules or so. And so of course now we want the total energy of this transformation. So our total E now we can just add up all our processes. So starting with our leg 1, so 6.99 kilojoules plus 30 kilojoules plus 3.29 kilojoules so let's see what that gives us. So 6.99 plus 30 plus 3.29. So then we should get that the total energy required for this process is about 40.3 kilojoules. So any questions about that? So on an exam, what I would just be prepared to do is just be prepared to kind of do this for any substance. So on an exam, I would give you, the delta heat of fusion, vaporization, heat capacities, all that. So I don't want you to waste your time on your exam trying to Google it, especially since you can find all sorts of different numbers or little discrepancies. But on an exam, right, I would provide all that information, provide boiling point, melting point, all those parameters. But then it'd be up to you to figure out, well, where are we kind of on this heating curve? Just like we did here, we had to figure out, okay, we started off in the liquid phase and then go from there, or, some other scenario. And then, of course, if we were going the opposite way, just know that it would be heat loss, right? So then you could have also said, what does it take to go from 100 degrees Celsius to 0 for acetone? It'd be the same process, basically, except backwards. So I think we've covered everything. Unless there are questions or anything. Scroll down where you need. So we'll probably end lecture around there for today, unless there are other questions. Questions on homework, questions on gases, moles, anything. Watching the chat too for questions. Otherwise, enjoy your 3-day weekend. So I'll leave the screen up for a little bit as people copy down. And I'll take any questions.
Who else works out the weekend?
No.
Do you? I said, who else works out the weekend? They both said no. What did you say? Also no? Wow, just me then. Fun. 4 p.m. to 12:30, Friday through Saturday. That'd be so much fun. Alright, you said you weren't taking summer classes, right?
All right, thank you, chat.
You should look into it at some point. They have fun classes. I'm doing kayak.
I'll hang around on stream just for a little bit longer in case there are any other questions. And of course, you can always email me, set up individual appointments.
You want a sour gumbo?
All right, thanks again, chat. I'm going to end the stream.